Welcome back. Today, in continuation of what we have done in the other lectures, I will talk about the potential energy in an external field. And the first of all, I will take the case of a single charge Q, which is put in an external electric field. Well, obviously we are going to answer a question. What is the potential energy of a charge Q in a given electric field? Now, our charge Q is kind of mentally separated from the set of charges which are responsible for the given electric field. Okay? This electric field is due to a charge, due to a set of charges, an ensemble of charges, a distribution of charges, other than Q. For example, we can have the system of charges. Also, in case we deal in several charges, then for Q we will have Q1, Q2, Q3, etc. what comprise the system. Okay. What we care for, and this is very important, what I am going to talk to you today slowly is very important. It's very significant. This requires your training deep into the electric field and the potential system, wherein we are going to talk about the potential energy associated with the charge when the charge is in an external field. Okay. Now, I am going to make a statement. And the statement is that we care for the electric field or the potential profile. That's enough for us. I am writing the Arabic word bus. Enough is enough. So how come this becomes bus? It becomes bus because we have to bear in mind that by Mr. Small q, our charge under consideration is not going to cause any disturbance at all, either in the configuration or in the values of EV, etc. are not going to be disturbed at all by Q. So the Q has to be very small, infinitesimally small. Okay. Doesn't matter, you can take other values also, because we have been taking the value of 1 coulomb. Oh, 1 coulomb. Okay. No, I don't subscribe to that. I've said it again and again. So, friends, there is some space where the Q has been put, and in that space we have an electric field and a potential profile which changes from point to point, which may change from point to point, from time to time. Okay. So it can be time independent, it can be time dependent. Okay. The more you make it dependent on things, the more cumbersome will be the calculations. Okay. Now we have a point P with a defined coordinate for that point P, and that is R, the vector R. No problem. So let me write the potential energy of Q at R in an external field. That will be equal to the charge Q multiplied by the potential at this point R. Very simple. Okay. So wherever there is a potential at any point, if we put that Q, or we can even change the value of Q and put that value, then we'll get the, so what is there? The charge multiplied by the potential. Okay, the charge multiplied by the potential. What is it? It is the potential energy. So if we take the potential difference between 2 points, of course we can find out the work done, Q into V1 minus V2 or V2 minus V1 or whatever. Okay, we will see that in the due course of time. Now let me define an electron volt. Electron is the basic charge. The electron charge is 1.6 into 10 to the power of minus 19 coulombs with the minus sign. Okay. Suppose we take an electron, we make the electron to travel through a potential difference of 1 volt. Then the energy that will be there is called E multiplied by V, electron volt, which turns out to be 1.6 into 10 to the power of minus 19 coulomb into volts, and coulomb into volts is joules. So this unit is a small unit. Okay, so that, well, for an electron we know the mass, and we know its energy in electron volts. What is this? KeV, K for kilo. MeV, M for mega. GeV, G for giga. TeV, T for tera. 10 to the power of 10 to the power of 3, 10 to the power of 6, 10 to the power of 9, 10 to the power 12, etc. Okay. So the particles, charged particles, they may have energies in this range. So what is basically happening? If suppose I have a small this thing wherein we can have a potential difference. I have a potential difference, delta V. Okay. And let this charge be positive. And let this potential fall as it is. So what will happen? This will experience a force. This will experience a force and when any mass particle experiences a force, associated with that is that in the Newtonian mechanics, F is equal to ma. So there is an acceleration. Okay. And this acceleration we can take, if we take that to be a constant, okay, then our life becomes easier. So what happens is that we have, if the mass is known and if the energy is known, if the entire energy is converted into kinetic energy from velocity 0 to velocity v, then there will be, this expression will come into being, half mv square. And then if the acceleration a is constant, then we have a set of equations here. You know that. V is equal to u plus at, s is equal to ut plus half at square, and v square is equal to u square plus 2as. So these are certain things, tools, with which we can open the problem. We can solve the problem. We can analyze and synthesize the problem under consideration. Of course, there is one more thing, and that is this mv square upon r. What is that? This is the centripetal force, which has to be provided by some actual force. So in that case, what we can make is, we can make the particle go round in a circle. Now I'll tell you something, okay? I will tell you something. And that something is that once upon a time, what was needed was very fast particles. And maybe the particles are protons or some kind of ions like helium, doubly ionized helium, or anything like that, even electrons. So what we want is that they should be accelerated. So if there is a positive charge, and this point there is some potential, and here there is another potential. So this potential minus this potential is positive. So what happens to our positive charge? This positive charge will be accelerated like this. Okay. And this is done, we'll see, by a pair of plates, like in the case of capacitor. And this is done, then this emerges out of this side, and then again we apply another potential difference, another potential difference, another potential difference. So linear accelerators, 5 mile long, 3 mile long, etc., were once upon a time a fashion until the cyclotron came. And in cyclotron, actually these distances of miles, with the beauty of the design of the cyclotron, the mathematics is very easy. I have taught you all mathematics which is required. Then they had 2 Ds. Between the Ds, the charge was projected, and the charge will go in a path like this. When it comes to this end, this will again be accelerated through a very small distance, okay, between the Ds, and then again it will take a longer radius and going like this, okay. Finally the charge becomes very, very fast. That mass becomes very, very fast, and these charges can be used as for collisions with other things which are objects which has to be collided with this very fast charge. Okay, so this very small thing that I am trying to tell you about is actually the mother of many experiments which have been conducted. Many cyclotrons, this tron, that tron, etc. And the mathematics all depends upon a set of these things which are in the domain of Newtonian mechanics, which you have learned so far. So next item, we take a system of 2 charges, Q1, Q2 at R1 and R2, and see as to what will be the total energy of the system if these 2 charges are held at R1 and R2. They are brought from infinity, and the potential energy associated with them we are going to talk about. So next we take another simple case, system of 2 charges, and I will expect you to extend it to a system of 3, 4, 5, 6, as many as you want. Okay, I'll just tell you the way. Now, I have a system of these 2 charges which are located at the position R1 and R2, which are the coordinates of this. And here around, I have only these 2 charges, and I have an electric field and a potential profile with the various points around, this point also and this point also. And we have the constraint that these two charges, they are not going to disturb the reason for the electric field and the potential profile. So with those two constraints, it's very simple. Let's have only Q1 and try to bring it from infinity to this point A. So the work done will be equal to how much? Value of the charge multiplied by the potential at this point R1. Then step 2, I bring the charge Q2 from infinity to the point P. Okay. So one of the factors in the work done will be equal to Q2 VR2. But Mr. Q1 will say that, well, you will have to work against my field also, against my potential distribution also. And in that case, we have learnt it before that the two charges Q1 and Q2, an additional work has to be done, which is 1 upon 4 pi epsilon naught Q1 Q2 upon R1. Okay. So now we have this and this, and the potential energy of the system of two charges, in assembling them to the positions A and B under the influence of the external electric field, are the mapped potential at those points around at a certain moment of time, if they are varying with time, etc. But we are not going to take that. Okay. So I'll write this as equal to Q1V R1 plus Q2 V R2 plus 1 upon 4 pi epsilon naught Q1 Q2 1 upon R1 2. Well, if I extend it from 2 to 3, okay, I have a charge here at the point C located at R3, okay, and the value of the charge is Q3, etc. Then we will have Q1 VR1 plus Q2 VR2, okay, plus Q3 VR3 plus 1 upon 4 pi epsilon naught Q1 Q2 upon R1 2 plus 1 upon 4 pi epsilon naught Q2 Q3 R2 3, etc., etc. Okay. So this you can work out. Think that you don't leave anything, okay, and you have to do that kind of a mental exercise. So with that, this is how we deal in a system of charges after we have dealt in and with the single charge. And now let us have a dipole. A dipole minus Q to plus Q. I have shown this with the green line is the dipole moment vector. Okay, this is the center of the dipole. This is 2A from here to here. This is from here to here. It is A. From here to here it is A. And with the x-axis that we have chosen here, it makes an angle of theta. Right now in the position that we are dealing in. So what happens is that there are two forces. I am not writing force and force. Okay. They are equal and opposite. Equal and opposite. Therefore, the net force for the system that is there is equal to 0. However, there will be a torque. And this torque will try to bring it either this way or this way. That all depends upon us. What we want to calculate. So there is a torque. Tau is equal to P cross E. Vector P cross vector P. Vector P is the dipole moment vector. and the electric field which is present over here, which has been shown to be a parallel set of lines. Okay, so there is a uniformity, etc. We have made our life safer. Okay. Then, now, if we want to change it from an angle theta 0 to theta 1, okay, that is rotate P in the plane of the board. This is the plane of the board. For you it becomes the plane of your notebook or copy. So, this external force, torque external, neutralizes tau. And therefore, this has to be rotated from any given angle theta 0 to theta 1. I'll tell you what is the convenient thing, so that there is this from here to here, it is a cos of theta. From here to here, it is a cos of theta. Total becomes equal to the distance between these two forces. It becomes such that, okay, of course, we will have this value as sine theta, a sine theta, and a sine theta, etc., etc. So, what is the job of this external torque? Is to neutralize this torque, and thereafter we have to bring the angle of the, bring the dipole from a location of angle theta 0 to theta 1 or theta or whatever you want to say. One of the safest things that I'll just will find is that theta 0 is taken as 90 degrees. Is good choice, because cos of 90 degrees is going to be equal to 0. Okay, and therefore now I am going to complete the calculations over here in this space. I'll rub it off and do it for you. Okay, so carrying out the mathematical analysis through the case of the dipole in this field, and I told you that this is a cos of theta, this is a cos of theta. Okay, but here, from here to here, it's a sine of theta and a sine of theta. So the total separation between these two set of forces, where I have not written F, that will be equal to 2a sine theta multiplied by q, and you will get the torque. Now, work done by the external torque will be equal to, if we take it from an angle of theta 0 to theta 1, then its value of the torque at the angle theta, d theta, theta 0 to theta 1. This turns out to be like this, because this will turn out to be equal to P e sine of theta. Okay, where P is equal to 2a into q. Okay. So when I carry out the integration, okay, then because integral of cos theta d theta is equal to minus sine theta, so putting those values, I'll get P e cos of theta 0 minus cos of theta 1. Now this work done is stored as the potential energy u theta with the choice of theta 0, this is our choice, which we have taken as pi by 2, and the cosine of pi by 2 is equal to 0. So our life becomes easier. Okay. So this becomes equal to Pe here, cos of pi by 2 minus cos of theta. So that becomes equal to 0 minus cos theta, so I get it minus P cos of theta, which is the value of P dot E, okay, minus P dot E, okay. And of course theta 0 has been taken as equal to pi by 2, and when that choice is there, then we can we can write it as u theta is equal to minus p dot e and calculate that value given the value of p and e and the angle there, etc. The same conclusion can be made from the equation that we had for two charges, okay, q1 and q2, just in the same lecture. So u is equal to q1 v1 r1 plus this. This is what we obtained. Now there is a displacement parallel to the force, and displacement parallel to this force is equal to a cos of theta plus a cos of theta is equal to 2a cos of theta. So I can write the value of VR1 minus VR2. Some of the students, they may be confused because I have taken a vector over here, so they may think that these are vectors, but no, I am having the potential and potential here, so there is no question of vector. So that turns out to be equal to minus E into 2a cos of theta. Now let us try to obtain the potential energy associated with that and write it as U dash. So this is equal to minus P cos of theta minus Q square upon 4 pi epsilon naught multiplied by 2a, the distance between the two charges, minus Q and plus Q. Okay. So I can write this as minus P dot E, okay, like here, okay, minus P dot E minus Q square upon 4 pi epsilon naught into 2a, okay, this is equal to minus P dot E, just like what we obtained over here. So this result and this result are one and the same, okay. Now this term for whatever we have for the dipole, Q square is a constant, 2a is a constant, 1 upon 4 pi epsilon naught, this is also constant. Always remember that value 1 upon 4 pi epsilon naught is equal to 9 to the power 9, the units that we have, and this is a constant. So when actually we are going for the potential energy difference, then this constant term can be dropped. So being a constant, this term is dropped, and therefore the value that we'll have as u theta will be equal to minus P dot E, minus P dot E. And here I finish off with this thing. I may return to some calculations later on, okay, when I end the chapter. We can calculate as to what is the and a similar kind of thing, similar kind of mathematics is also done in the case of magnetic dipole. So there I can recall things, do it faster, and for you it's an understanding which is similar to this case, in that case also. Next we'll talk about the electrostatics of conductors and learn various things which are very, very important to us for application when the conductors are present. Okay, then I will also talk about non-conductors when they are present, and what we will talk about is dielectrics also. Okay, so thank you very much for today, and remember this. Okay, remember this, that you question, we answer. We are ready, sitting on our desk, to obtain your questions and to solve them and be back to you with the answers. Thank you very much. See you.